right, the questions. Number 1. Was the correct order from hottest to coldest stars for star spectral classes? A. What was the mnemonic I taught you?
The only bad astronomers forget generally.
Only bad astronomers forget generally known mnemonics like this. Now, I was reading in preparation, and there is now yet another Y at the end. So, yo. That's what it says in the textbook if you read it.
Yo.
It says, instead of, oh, be a fine gal, it says, oh, be a fine girl. Kiss me like this. Yo. Something to add to this. The L, T, and Y, you know what those aren't? Those aren't stars. They're brown dwarfs. Brown dwarfs are something between a star and a planet. Almost all brown dwarfs are about the same size as Jupiter, but they have masses that start about 13 times the mass of Jupiter. If Jupiter was 13 times more massive, instead of being considered a planet, it would be considered a brown dwarf. What's the difference? Well, to be a star, you have to be fusing hydrogen to helium. Planets don't. The brown dwarfs reach a high enough temperature where they can fuse deuterium, but not hydrogen. Deuterium is hydrogen 2. And so they have some fusion that occurs, but not fusion of hydrogen 1. So that's the distinction. Brown dwarfs have some fusion, but not fusion of hydrogen 1. All right, so we got that. And you'll notice that this one here was alphabetical order, and that one was reverse alphabetical order. The original classification was A, B, C, D, E, blah, 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 based on how strong the absorption lines of hydrogen were. And then it was Annie Jump Cannon who said, well, that doesn't make sense. The guy who did it realized that there were some problems, and so she rearranged them, taking some of the letters he had used into putting them in order of hottest to coolest. So A's would be the ones that have the strongest hydrogen absorption lines in the spectrum. And then B's would be next, then C's, D's, E's. And I'll actually show a picture and we can look at it. Okay, number 2. 2 stars are observed, star A. This was, of course, one of the questions I asked in class, as was the next one as well. So if star A has a magnitude of 4 and star B has a magnitude of 2, which statement has to be true? There are 2 others that could be true, but there's one that has to be true, and there's one that has to be wrong. So what does the apparent visual magnitude tell you, first of all? What property? Brightness. So we can immediately rule out the 2 luminosity ones. Either one of these could be true. And then we go to, what does it tell us about brightness? What's brighter? A higher number, like 6, or a lower number, like 1? Lower numbers. So the brighter one is the one with the lower magnitude, which was B. And so that was answer B. Number 3. How supplies. What supplies the power radiated by the sun? Okay, we have C, nuclear fusion. At least one person had put fission. What's the difference in fission and fusion? Fission is a big thing breaking into smaller pieces. Fusion is smaller things merging to form something bigger. Combustion, what is combustion? That's a fire. So when you have a fuel, you have an oxidizer, and you have a heat source, it makes fire. That's not what's going on with the sun. And it reflects light from other objects? No, but what does reflect light from other objects? Planets, the moon. All right, final one. Anybody see a pattern? I thought I was funny.
Oh my
Yeah.
God.
How do we know that the sun has a convection zone? Granules on the photosphere exhibit signs of convective currents. You have the granules, by using the Doppler shifts, we can see, that material is moving toward us, and it's hotter by looking at the spectrum. On the edges where it's darker, we can see, it's moving away from us, and it's cooler. And let's say, it definitely has some convection going on there at the surface. So we know for sure that it has a convective zone. Any questions about the quiz? Yeah.
Just to confirm, neutrinos is used to determine if there's fusion going on in the center of the sun, correct?
Neutrinos are evidence of the fusion, and we now, with our better understanding of neutrinos, we actually have the right number of neutrinos for how many fusion events we think are going on per second.
Okay.
So those are signs of fusion, not of convection. And that is what you asked. Just for the record, usually I have it randomized the answers and the questions, not once but twice, just to make sure it's truly random, except for my physics exams where the questions have the answers in alphabetical order. So it just comes out whatever way it plays out alphabetically, just in case you're looking for the patterns in my questions or in my answers. All right. Alex, you asked if we could look at a specific homework problem. Which one was it?
6 and 7.
Okay, I thought I heard 67. I was like, there ain't no 67, so that's...
No, they're not. They put
Whoops. I was too slow in pressing my button. I'll do it faster. There we go. Okay, and then it failed. Thank you.
Yes, physics.
It is physics, and it rocks. This time, it works.
That would be geothermal.
What?
Yeah.
See where you're going now. Okay, so here I'm just copying and pasting the two questions Alex mentioned. Okay, let's not delete the quiz. Okay, so here's the two questions Alex asked about. Number 6, show that the statement that 92% of the sun's atoms are hydrogen is consistent with the statement that 73% of the sun's mass is made up of hydrogen, as found in some link that actually does work from the webpage. Hit, make the simplifying assumption, which is nearly correct, that the sun is made up entirely of hydrogen and helium. All right, so how do we go about doing this? How many people have questions about how to go about doing this? Okay, slim majority. So what we do is we say hydrogen has one thing in the nucleus. So it has mass of hydrogen is equal to 1 atomic mass unit. Helium, remember when we went over the periodic table a long time ago? Helium has 4 things in the nucleus. 2 protons, 2 neutrons. So the mass of helium is equal to 4 atomic mass units. So now we're just going to take this statement and say, okay, 73%, well, actually, that was the second number. 92% of the atoms are hydrogen. So mass is equal to 0.92 times the mass of hydrogen plus 0.08 times the mass of helium. Right, that would be how you calculate the total mass. And so then the percent hydrogen by mass would be 0.92 times the mass of a hydrogen divided by the total mass. Right, how much mass in hydrogen divided by how much is the total mass? So I really need to calculate 0.92 times 1 is 0.92. And this one here then, 0.92 plus 0.08 times 4 is 0.32. So that gives me 1.24 atomic mass units. Now, what I've done is taken percentage. So this number is not really atomic mass units, but it tells me about the mixture, the total mass. If I knew how many atoms of hydrogen I would have, the total. So then I just have 0.92 divided by 1.24. It's what?
0.7.
Yeah. So in too much space, I've shown now it said 73%, I got 74%. We only had, 2 digits there in our numbers. So I'm very happy with that being off by 1 in the last digit. Question, Alex?
I'm still processing.
This is 0.92 times, if you want to be technical, the number of atoms in the sun would be multiplied by everything. So this would be 1.24 atomic mass units times the mass of the atoms or times the number of atoms in the sun if I were to do it accurately. And likewise, I would have the same thing here. And the number of atoms in the sun would cancel out. Mira.
Can I change my answer?
Absolutely. All right. You still working on it there, Alex?
Yeah.
I do want to make sure I give you time to actually digest what I said and not just go on.
How did you know that's exactly what you needed to do?
How did I know that's exactly what I needed to do? My brain told me so, which sounds really lame, right? I wanted to go from number of atoms to mass. And so I used the mass of an atom because that's the thing that connects the two. And so I took the fraction of the total atoms, 0.92 for hydrogen. I should have put times n, the total number of atoms, because then that tells me how many atoms I have of hydrogen, multiplied by the mass of hydrogen, and that tells me the total mass of hydrogen. Same thing for helium. Add them together gives me the total mass of the sun, then take the ratio. And of course, part of that error I have is probably due to the fact that the sun is not all hydrogen and helium. Okay, he said 6 and 7. Number 7, the escape velocity from any astronomical object can be calculated from V escape is square root of 2 gm over r, where r is the distance from the center that the object is, m is the mass of the thing that you're escaping from, and g is a constant. Calculate the escape velocity from the photosphere of the sun. So I'm going to need to look up r will be the radius for the photosphere of the sun. Can I count on you again, Juliet, to look up the numbers? Mm-hmm. So what is the radius of the sun? If you look up radius of the sun, it's going to give you the radius of the photosphere.
Okay, the radius of the sun?
Yeah.
In miles or kilometers?
In kilometers will work.
Okay, 696,000.
So I converted that to meters, so 696 million meters. So there's the radius. The mass of the sun is 2 times 10 to the 30th kilograms. I just randomly know that. So those are the two numbers that I need. So then I just put that into my equation. V escape is equal to the square root of 2 times g, which is a constant 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. To the 30. So there's G. Then I need to put my mass. So took away the square root so I have room to put the mass. all over the radius, which is 6.96 times 10 to the 8th meters. And then I just put that in the old calculator, which I usually don't do. I want students to do their own calculation, but I'm just curious enough that I have to do it. According to my quick calculation, which if I'm wrong and you write down and it's wrong, you would get it wrong, right? You can't just trust me. You have to do it yourself. That's what I got. Hopefully I did it right, but I could have made a mistake. So make sure you do your own calculation. But all you had to do is put the numbers in, just look them up. And of course, there's always the chance that Juliet was messing with us so all y'all would get it wrong if you just wrote the number down. I don't think she would. There's the chance. You got a different number?
Yes. Well, it's slightly different number than a 2.0, so I have 1.98.
Okay, that's the way you do it. Make sure you get accurate numbers and do your math accurately. And like I said, I trust that I did it right, but I would always double check. All right, there's a couple homework problems. We're halfway through the lecture. Maybe it's time to look at some new content. Maybe. Okay, you've seen this picture before. Now you understand what it is. You also can understand why I did not have this visible during the quiz, because you could have just read it. Oh, be a fine gal, kiss me. Like this, yo. So if you look at this, you can see the A's have the strongest hydrogen lines because that was the original naming structure. And the B's are just a little weaker. And then the F's are a little weaker. G's are still weaker. Right, the hydrogen lines are this one here, this one here. There's more, but there are those two. So I'm using those as references, and you can see how the original organization was. And then Annie-Jump Cannon switched things because hydrogen lines are strongest not at highest temperature, but at around about 10,000 kelvins. And so the A should be somewhere in that ballpark. So here's the list. Now I have the list twice. This one's from a different textbook, then the next one's from our textbook. The fundamental difference is that the next one has the, like this yo on it. So temperatures, O's are above 30,000 Kelvin. And for O's, you have ionized helium and weak hydrogen absorption lines. Weak hydrogen absorption lines. Then B's, 10,000 to 30,000 kelvins, and you have hydrogen absorption lines are reasonably strong. I mean, after all, B would be the second strongest group. And neutral helium is strong. Get down to A's, 7,500 to 10,000, the strongest hydrogen absorption lines because it's A. Then keep going to F, 6,000 to 7,500. Weaker hydrogen again because you're going back down. And it has metals. What's a metal in astronomy? Anything besides hydrogen and helium. So when it says metals, we're talking about anything besides hydrogen and helium. The metals, especially ionized calcium, have some peaks. And then we get down to G's. What's special about G stars? The sun is 5,800 kelvins. It's on the hot side of the G spectrum, which makes it a G2. So that's the range we're in. It has ionized calcium absorption that's very strong and pretty weak hydrogen absorption now by the time you get to our sun. Keep going to Ks, 3,500 to 5,000. Ms, 2,000, 3,500. Ls, 1,300 to 2,000. Ts. Notice I had question marks here. Let's go to the next one because our textbook is newer. And we can look here. Ls, it has 1,300 to 2,400. T, 700 to 1,300. And yo, less than 700. 700 kelvins. How hot is that? Room temperature is about 300 kelvins. Boiling water is about 400, that's 373 kelvins. So it's hotter than boiling water, but not a lot hotter. So it's not super crazy hot. We make things hotter than that on Earth. So these down here, the bottom three, like this yo, are brown dwarfs. Example of a brown dwarf I talk about a lot, Proxima Centauri. I call it a star, the closest star. Maybe we should say quasi-star, right? Because brown dwarfs aren't really stars because they don't have hydrogen fusion lighting them up. Everything above that, the M's and higher, those are stars. And here's some examples of stars in each category. So you see Rigel. Does anybody remember where Rigel is? Where is it? It's the front foot of Orion. So that is a B star. B stars are very massive stars that are very hot. Then we have type A stars. The two brightest stars in the sky, Sirius and Vega, are A's. Type F's, Procyon I should be able to point out, but I would have to go look. I don't remember exactly what it is. Canopus, I don't know. G stars, well, hey, look, the sun. And Capella, which I always want to call a cappella, but it's not. Ks. We're getting into Ks. We're starting to get into red stars. Arcturus and Aldebaran are red giants. Betelgeuse, Antares, red giants. And then the ones below are in the brown dwarfs. This here is showing the relative strengths of the absorption lines that were in the previous two tables. And so you can see by temperature, we're a G2. So a G2 is going to be about here. And so we're going to have strong metals, weaker neutral metal, and fairly weak hydrogen absorption. And so it's looking at the relative strengths of these things that allows astronomers to pinpoint the temperatures accurately. Obviously, you don't have clickers to answer this. Our sun is a G2. What does that tell you about its temperature? Yeah, it's mid-level. It is cool compared to some stars, but it's hot compared to others. So it's mid-level. Go forward. There we go. Now, I'm going through this in a different order than the textbook. I'm covering stuff from a couple chapters here, 17 and 18, I think. Maybe it's in 19. So in my organization, I'm going to go straight to binary stars. Binary stars are stars where you have two instead of one in your system. So our solar system has one star, Sol, right? A binary system would have two stars. For instance, you could have Sirius A and Sirius B. Two stars. Do these occur regularly? What do you think? Okay, Juliet shook her head at this, right? And she said she didn't think that they were very common. It turns out that they are extremely common. In fact, somewhere between 1/3 and 1/2 of all stars are believed to be parts of a binary system rather than by themselves. So they're really common. The fact that we are not part of one, well, single stars are also common. We break these binaries down to 3 different types, and those types are based on our observation. That's it, just based on our observation. They're not based on anything special going on with them. So visual binary is a binary star that if we get a telescope and look at it, we can see, hey, that's not one star, that's two. And we can track them as they move around each other. So visual binaries are stars that using a telescope, we can actually tell that's two objects. I can distinguish one object from the other, and we can track their motion. Then we have spectroscopic binaries. Spectroscopic means we're going to look at the spectra from the stars. And by looking at the spectra, we can see that there are two stars. How would you know? Because you have two different sets of spectra, and if you look at the absorption lines, when one's coming toward you, the other one's going away from you. And so, like the hydrogen emission or absorption lines will be split, and they'll move back and forth as they alternate which one's coming toward you and which one's going away. So you can tell by looking at the changes in the spectra that you have two stars that are going around each other. You can't see the two stars, but from the light you can tell. And then the last one is if you have two binary stars that are orbiting and their plane of orbit is just in line with our line of sight, so that one passes in front of the other as we view it. That's not that common because you have to have just the right alignment. And in that case, we call it an eclipsing binary. Just like when we have a lunar eclipse or a solar eclipse, we have one thing passing in front of the other. So the eclipsing binary is a special category, and you can have either a visual or a spectroscopic be eclipsing. So here's an example of what you see when you look at the spectra of a spectroscopic binary. Notice you have, this is just looking at a single absorption line, and you see the absorption line from star A that's coming toward you. Because it's coming toward you, it's shifted toward the blue. You also see the same line from star B that's going away from you. It's shifted toward the red. Then when they're passing like this, so neither one is coming toward you or away from you, they're on top of each other, so you just see one line. And then they switch the other way, so now B is shifted to the blue and A is shifted to the red. So you see those lines moving back and forth, and it tells you, aha, this thing is sometimes coming closer and sometimes going away. Now keep in mind, if it's eclipsing, you know exactly it's coming toward you. So when you measure the speed, you know exactly how fast it's going. If it's not eclipsing, you don't know exactly how fast it's going. It could be tilted like this or like this or like, you're only measuring the component toward you, so you just have a minimum speed. You know if it's not eclipsing, it's going faster than that speed, you just have a minimum. Here's a graph showing the position or the relative speeds of the stars as a function of time. Looking at the shifts, notice this is at 40. Radial velocity of plus 40. Doesn't give us the units, but I'll just leave it at plus 40. That means that the system is moving away from us. I assume plus means away. It does say kilometers per second. At 40 kilometers per second. So the system of the two stars is moving away at 40 kilometers per second. And then you have star B, there at 4 days, is moving away from us at about 100, between friends, 100 kilometers per second. Which means relative to the motion of the center of mass of the two stars, it's going 60 kilometers per second away from us, relative to the center of mass. Whereas star A is only moving away from us about 15 kilometers per second, or relative to the center of mass, it's coming toward us at 25 kilometers per second. Why would star A not have a radial velocity as big as star B?
It might be the heavier one.
It's the more massive one. The more massive one isn't going to move as much. They both have the same tug on them, but imagine if it's all on and me. If all on and me push off of each other, who's going to move more? It'll be all on because he's lighter. And that's what's happening with the stars. The lighter star does a lot more moving than the heavier one. So all on was right on. That tells us that A is the more massive of the two stars. In fact, by analyzing that, we can get a ratio. We can determine the mass of a system if we can measure the period and the semi-major axis. Semi-major axis is the average size of the orbit. So if we can measure that semi-major axis, then we can determine what the mass of the entire system is. It's the mass of both stars together. Now, of course, you need to be a little careful to get that actual semi-major axis. It's not real simple. That gives you the sum of the two masses. So by itself, it doesn't tell you the mass of either star. It just tells you the two of them together have this mass. So the next step is basically the idea of a teeter-totter, of a balance. If you have two stars, they're going to orbit what we call the barycenter, the center of mass. And so, once again, using the example of all Juan and me, if we were stars and we were orbiting based on gravity, because I'm more massive, I wouldn't be moving as much, the center of mass would be closer to me. And so from that graph we had of the velocities, we could actually determine from that, from the, not the velocities, well, it was, from the redshifts, we can determine where the center of mass is, and then we can get the ratio of the masses based on the ratio of the distances they get from the center of mass. And so if you can measure the ratio of the masses, and you know the total mass, then you can know the mass of each star. And so scientists do this very regularly. We're not going to do the math, but you need to know there's a process here. I put this one in. I don't think it's in our textbook. Spectral interferometry. Interferometry is when you take two telescopes that are separated by a large distance and you combine the information. When you do that, you can get a resolution that is similar to what you would have if you had a telescope equal in size to the separation of the two telescopes. So if you take like one telescope on Earth and one telescope orbiting the Earth and you use interferometry between them, it's like you have a really large telescope, which makes your resolution, you can see much smaller things. And so using spectral interferometry, we can image a few stars. And really, it's a few. It's not a lot of stars. But then you could actually get a direct measurement of the size of a star. Very rare. Other ways of determining the sizes of stars. If you have an eclipsing binary, if one passes in front of the other, when the cooler one passes in front of the hotter one, then you're going to have a diminished luminosity. Diminished because the cooler one doesn't put off as much energy per unit area as the hotter one. Now, if the hotter one passes in front of the cooler one, it's still going to be dimmed, but not as much. The hotter one is putting off more energy per unit area, but it's also blocking some from the cooler one. And so you're losing a small amount from the cooler one, whereas if the cooler one passes in front of the hotter one, you're losing a lot more. So you can look at this and you can see this here is when the cooler one passes, hotter one passes in front. This one here is when the cooler one passes in front. And you can determine, if you know how fast the stars are orbiting each other, then you can determine the size, because it has this marked here, it doesn't have everything. Going from Mark 2 to Mark 3, the time that it starts to dim to the time that it starts to brighten up, that's the time it took for the star to pass in front of one star to pass in front of the other. From when it just started on one side to when it just came out on the other. So if you know the speed and you know the time, then you can calculate the size of the bigger star. And then you can take the difference between this, the time between when it starts to dim and when it reaches maximum dimness, and that tells you the time it took for the smaller star to cross over. So once again, in the same method, you can determine the size of the smaller star. So if you have an eclipsing binary, you can use the time information from that to determine the size of the stars if you know the speed. But once again, it has to be eclipsing, means perfect alignment. When is the light going to be the faintest? When you have the hotter star in front or the cooler star in front? Cooler star in front, because it's blocking the greater energy per unit area of the hotter star. Okay, we've already seen the stuff on Boltzmann law, the thing that relates luminosity to temperature. And now I put in the equation for the surface area of a sphere. The surface area of a sphere is 4 pi r squared. So previously I had just put A where this occurred. But now we can see that the luminosity depends on two variables. Radius to the squared, well, radius to the squared, yeah. Let me not say to that. Radius squared and temperature to the 4th power. So hotter stars emit more light, bigger stars emit more light. You double the temperature, it's 16 times more light. You double the radius, it's only 4 times more light. So it's more sensitive to temperature. That's going to come back in just a moment. That's not a lost idea. If we look at the stars near Earth, near our sun, probably a better reference point, within 21 light years, this is all of the stars that have been discovered as of 2015. And what you see is, well, what do we have the most number in? M's. What can you tell me about M-type star, M spectral class stars? Okay, you said barely, right?
Yeah.
Yeah. They're the coolest stars. They're the coolest full-fledged stars. We call them red dwarfs. Red because red is the color of the coolest stars. Dwarfs because they're small things. So the vast majority of the stars in our neighborhood are red dwarfs. And then we look up there, 17Ks, 7Gs. We're fairly rare. We're a G, right? And then there's 1 F and 2 A's. We're on the large side of the stars in our neighborhood. And we assume that this is probably pretty uniform throughout the universe. That there are a lot more small stars than big stars. Or maybe I should have said, because you don't know this yet, a lot more cool stars than hot stars. White dwarfs. I know it says dwarfs there. I copied it from the book. But everybody knows the Snow White and the 7 dwarfs. Dwarfs is the plural of dwarf. So, anybody know what a white dwarf is? Not of a supernova, but it is the remains of a dead star. White dwarfs are the remains of stars under 3 solar masses during their lifetimes. Under 1.4 solar masses at death. Stars, during their final stages, they blow off a lot of mass. So that's why there's the discrepancy there between them. A white dwarf cannot be more than 1.4 solar masses. That's the Chandrasekhar limit. But they form from stars that are more massive, that lose mass during their death. So those are dead stars. Brown dwarfs, not quite enough mass to be a full-fledged star. There's probably a lot more brown dwarfs. They're hard to locate because they don't give off much of any radiation. So what we need is some way of organizing these stars. And 2 scientists, independently, one's last name is Hertzsprung, one's last name is Russell. You can look at the book, there's a little bit of write-up at least about Russell. They said, well, what would really be useful to me would be if I were to categorize them with temperature on one axis and luminosity on the other. Luminosity is the total amount of light they give off. Temperature, of course, is clear. One thing to note here that's important. Temperature, which side is hot on the temperature spectrum? It has an arrow. This side here is hot. This side here is cool. What about bright or luminosity? Which side is more luminous, top or bottom? So this is the luminous, that's going to be good enough. And down here are the dim ones. So if you plot all the stars we find in the sky by that way, you find some organization now. Well, kind of. You have this thing here that we call the main sequence. Because the vast majority of stars are on that main sequence. It's a line, not a straight line, where we have most stars. These things down here, they're fairly hot but small. Those are white dwarfs. By the way, what should I call these things down here? Notice these are the M's and K's. So what would an M and K that doesn't give off much light be? Not giants, because they're not giving off much light. Giants, because they're large and give off a lot of light. So they're going to be red dwarfs. Where, going with what Alex said, these things up here would be red giants. Because they're giving off a lot of light at the same cool temperature. So we now have some kind of organization. Now we're going to learn in the coming weeks about why we have that organization. And I have like 7 different variations of the Hertzsprung-Russell diagram. You will, for your next quiz, you're going to draw a Hertzsprung-Russell diagram. You're going to label hot and cold temperatures. You're going to mark where the main sequence is and where the different luminosity classes are besides main sequence. So keep that in your head that this is going to be really important.
So what we just did now.
There's more to it, but what we're starting in on now. So notice again, temperature, hot on the left, cold on the right. Notice also that's not a linear temperature scale. That is, if you go from 3,000 to 5,000, that's the same distance as going from 20,000 to 30,000. So it's not a linear scale, it's a logarithmic scale. That's done intentionally, right? It's not just random. Vertical axis, likewise, that's a logarithmic scale. It's the same difference between 1 and 10 as it is between 10 to the 5th and 10 to the 6th. And now you can see white dwarfs is labeled here. And the red giants are labeled. So red giants are here. Okay, red giants, yellow giants, blue giants. Well, I'll keep the main sequence out of the blue giants. White dwarfs, and of course the main sequence is this here. Why did I put this equation on here again? Well, because of the logarithmic nature here, I'm going to have, if I take this equation, I solve it for radius, it will give me an equation that says that the radius is equal to a constant here that I'm not going to write times temperature squared over the square root of the luminosity. So I can determine the radius at any location here based on the temperature and luminosity. Wait, I did that backward. It would be square root of luminosity over the temperature squared. It's kind of important to get that right. So the next graph shows green lines for constant radii. The smallest radius is down here, and the largest radius is up here. So you can get radius from the HR diagram. So there's a lot of information, and there is more coming. Right? I told you this thing's really important. That's why you're going to have to be able to reproduce it. So what more is coming? What's coming up next is, I like my title there, Stars Come in All, what is that word? Sizes. What's coming up next, which we'll have to put off until Friday, is the luminosity classes. Luminosity classes are different classes of stars based on their luminosity. And so I'm going to start with this slide next class period. You all have a great day. I look forward to seeing you on Friday. As I presume